Welcome to the Alpha Training and Consulting's online training program. Today's lecture is entitled AI in Performance Management of Heavy Industrial Equipment. And the agenda for this lecture is, first we're going to review the basics of reliability engineering. And then we're going to go through these various topics. And they're listed here also. Artificial intelligence transforms the management and reliability of heavy industrial equipment through advanced analytics and automation. Key areas include predictive maintenance, failure mode effects analysis, reliability modeling and simulation, root cause analysis, spare parts optimization, human reliability, and warranty and field performance analysis, and reliability-centered design. So we're going to go over those topics and how AI impacts it. And I'm going to go over a program that we have that we're creating here at Alpha Quality Consulting. And I think you're going to be very impressed. And as I go over that, you'll understand how AI will impact asset management. All right, let's go over the basics of reliability engineering by solving a case study problem. Let's assume the CEO of your company asks the organization to launch a new process and announces that to be competitive, the new process must have a minimum of 99.95% reliability at any given point in time. That's a minimum. It can't go below that. That's what your company standard is. The CEO is assigned you to determine what the reliability standard needs to be for each of the assets to be able to meet this overall reliability standard or system reliability of 99.95 reliability. Now, let me explain some math in reliability engineering, very basic stuff. But in order for a system to work, let's say I want to fill this bucket full of water. Okay, so I put 6 valves in here. I know it makes no sense to have 6 valves, but hang in there with me. And for each one of these valves to work to fill this bucket up, valve 1 must work, and valve 2, and valve 3, and valve 4, and blah, 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 and valve 6. I call those AND statements. Valve 1 must work, and valve 2, and valve 3. So there's 6 AND statements in this system. And each asset reliability at this given point in time that we're studying this is 95%. We made the math simple. We made them all equal. Okay? In order to answer the question, what's the probability that this bucket will be filled with water, in other words, valve 1 and valve 2 and valve 3, etc. working, you multiply them all together. In other words, the way you add reliability up is you multiply it. And so we go 0.95, 6 times itself 6 times, gives us 73.5%. In other words, the probability of this system actually working and filling this bucket up is 73.5%. This is called system reliability. This is called component or asset reliability. Okay? And that's how we add reliabilities together. We multiply them. Okay, let's move on with the question here. After a thorough investigation, you discover that you have a total of 5,600 assets or AND statements, 5,600 AND statements. Let's summarize the information we have gathered thus far. Reliability standard, 99.95%. Number of assets is 5,600. This is enough information to start our calculations. The formula we will use is found here. Reliability standard, this standard, which is right here, is what we're talking about. Of course, we want it to be this. This is the system reliability. System reliability standard equals probability of all those AND statements. In other words, the reliability of the asset. That's what I'm talking about right there. That probability of the individuals, sum of the probabilities. So the system reliability equals the asset reliability to the power of the number of AND statements. That's what we did back here. This is 0.95 to the 6th power. That's all I'm doing is that equation right there. Pretty simple. Now we will enter the known information. We already know what we want the reliability to be. The company says it has to be 99.95%, so we put that there. Number of AND statements is 5,600, and I want to solve for this, probability of the AND statement. what is the probability of the individual assets need to be when we have 5,600 of them to meet this standard? That's what we're asking. So what I'm going to do is I'm going to multiply both exponents by 1 over 5,600. That will wipe this one out, and it will be 0.9995 to the power of 1 over 5,600. And so we do that, put it in our calculators and computers, and it gives us this. And it says every asset at any given point in time cannot be below this number, 0.7911. So every asset, and that other one was the valve, every valve must have a reliability of 0.7911. And so that's what you need to understand to fully appreciate what we're doing with this software. Now, before we put data into the software package, of course, we have to screen it to make sure it's good data. If not, it messes everything up, obviously. So we enter the data into the database. We check the data for Weibull, exponential, and normal distributions. If the R-squared is above 95%, then we accept and categorize the data as parametric data. If the R-squared is not above 90%, 95%, comes over here and we still plot it on SPC. And if the data is predictable, it's not showing any unnatural trends, then we accept and categorize the data as non-parametric data. And then we do analyze the data. If the data shows that it's not predictable, then it sends out a corrective action to the quality engineer and says investigate this, because this data is totally unpredictable. And when you're doing mathematics, you always check to see, is it measurable and is it predictable? So we do that with the data, and if it says no, it's not predictable, then the reliability engineer has to go investigate and find out why. Oftentimes it's a bad sensor, or the sensor isn't having a bad connection, or whatever the case may be, and that needs to be fixed. But notice we're protecting the database that we're going to do analysis off of. Once it gets in there, we feel very confident that it's good data and how to analyze it. So that's kind of the upfront part of the program. Now this is what you'll see as a client. You'll notice here's the system reliability. Okay, that's all of these reliabilities multiplied together here. 60.5%. That's not very good, because the reliability standard of the corporation is 99.5. That's why it's in red. And man, we've got a problem here. And the minimum component reliability is 0.79 and that 1.1. If a component violates this, it means that this is not holding its responsibility. It has to be a minimum of this at any given point in time. It needs to be replaced before this number, it goes below this number, or rebuild or whatever. Okay? And so when an asset goes below this number, it will turn brown, it will blink. Of course, you can make it whatever color you want, but in this case it's brown, because notice they're all below this number here. That's why they're all brown. Now there's one red, and I'll explain that here in a little bit. Now another thing that it does, for every sensor you put on your machine, maybe there's a vibration sensor, maybe there's a temperature sensor on a bearing housing, or maybe there's a pipe thickness sensor, or what's another one? Oil analysis sensor. And it analyzes all of this data, and it can do so on a daily basis if you want it to. And it performs an analysis and says, hey, on every sensor it performs an analysis. It says, hey, vibration from yesterday to today, it has changed. Okay, it has changed. Something's changing in this machine. And when that happens, the alpha risk is below 5%, which this one is, it turns red. And it tells you, hey, this is sending signals that it's going to fail sometime in the reasonable future. And it'll have a confidence interval to give you an idea of how much time you have. Okay, but it will do this on every sensor. So if this is your asset, you'd click on it, it'd have all the sensors on there with associated alpha risk. And if any of those alpha risks go below 5%, 5% or below, it will change it to red. This sends out a signal saying, hey, we're starting to enter the wear out area of the bathtub curve, of the reliability curve, failure curve, if you will. And so that sends out a signal for maintenance action, at least maintenance investigation. Start planning what you're going to do. Maybe it's time to start ordering the parts for the replacement, etc. Or at least checking inventory to make sure that's available. Now, I had to simplify this screen, obviously, because imagine having 5,600 assets, okay? It's more like a screen as big as a wall so that you can see all those. And that's how the program works. It's very visual, as you can see. And of course, your goal is to get it from here to here. So the reliability department has a huge job in this particular one. So they'll go and look and say, how long has it been running? We need to change it before this, and we need to order higher reliability parts, and we need to put them in parallel redundancy. And you kind of experiment around till you get everything to work and meet this number, and therefore this one either equals this or exceeds this. That's the goal. So program capabilities. Compare system reliability to reliability standard in real time. That's this compared to that. That's all that's saying. Publish individual asset reliabilities. There it is. So it'll give you all those on all 5,600. Calculate minimum reliabilities allowed for individual assets based off of the reliability standard. There it is. It publishes that number right there. And if any of these assets fall below that, it will turn it to a different color, in this case brown, blinking, telling you this is not holding its responsibility, holding up to its responsibility. Its reliability has fallen below this, and you need to figure out how you're going to keep that from happening in the future. All right. If an asset violates the minimum allowed reliability, the asset will become a blinking brown color. All sensor data will be analyzed on a predetermined time basis every day, every week, etc. And we'll help you know when to do that, depending on the equipment and the criticality and how much data we get, quite frankly. All sensor data will be analyzed on predetermined time basis, and if a statistically significant change is determined, the asset will change to red. This suggests the wear out period has begun, and we use very large sample sizes for this so we can detect change very quickly. So the time that we detect it to the time you experience failure, we try to give you as much time as possible. Now over time, the program will also give you a tolerance interval of when you should expect failure. 95% of the time it will take place between here and there, etc. The program will understand when planned maintenance activities take place during constant failure rate period and communicate with the reliability engineering concerning this issue. So, what you see a lot of times, people do planned maintenance activities during the constant failure rate period. Well, that would be like you have an airplane and the jet engine's going along, you take off and you're flying along and a bird flies into it. That's a special cause. It's unpredictable. A bird randomly flies into the engine, gets sucked in, and wipes out the engine. And maybe this engine should last 3,000 operating hours or whatever. But this happened at 1,000. Well, some organizations will say, oh, it failed at 1,000, we better replace it at 800. The problem with that is if you put in a new engine, it's as equally likely to suck in another bird. It doesn't matter how many hours are on there. Let me give you another example. The other day we had these valves that were automatically open and shut to deliver gases to the system. And if you had a leak, it created all kinds of problems. It was very dangerous. And so what would happen, these valves would work back and forth, but once in a while a piece of rust would fall off the pipe, get on the valve face, and it'd scratch it back and forth until it had a scratch all the way across, then you had a leak. And these are supposed to last 3 months, but this happened like 6 months. So they said we'd better replace it every 5 months. Well, even if you replace it every 5 months, a new valve is equally likely to get a piece of rust in it. So you need to investigate these situations where preventative maintenance is taking place during constant failure rate. And what the system does is spits out a corrective action to the reliability engineer, and they go check to say, hey, why are we doing preventative maintenance on this during constant failure rate? And they start investigating. They get a valve and they look at it and they swab it and send it in for analysis. It comes back and says, hey, that's iron. And it's like, how did I get a piece of iron on this, this Teflon valve? And so you start investigating. The only thing it come from is there's a steel pipe up there. Well, it must be getting old. And so you replace the pipe, put in a stainless steel or whatever so it works better over time. And next thing you know, your valves aren't failing. They'll go through the full 3 years. And that's how you need to do this. And this program will tell you when you are doing planned maintenance activity during constant failure rate so it can be investigated and fixed. The program will predict maintenance demand months ahead of time and suggest performing preventative maintenance on slower demand months to help you prepare for higher demand months. That's kind of hard to understand. Let me see if I can explain it better. So, the computer program with artificial intelligence looks at everything. And it looks out quite a ways. And it realizes, hey, you have all these tolerance intervals that suggest during this month, a lot of the tolerance intervals are in here. So there's a high probability that you'll be getting predictive maintenance signals that this machine's going down. And, reasonably calculatable, you can say, hey, this month's going to have more demand than we have maintenance resources. So the program will say what we recommend is you do not predictive maintenance on this machine right now, but you do preventative maintenance. And so since we have a little downtime this month, we're going to take the more critical ones, the ones that are more likely to fail, and we're going to we're going to replace those before we get the signal of failure. In other words, we're going to do preventative maintenance on these instead of predictive maintenance. So, and we're going to do enough of those to where we're going to try to flatten out the demand for maintenance activities. Try to make them constant as possible every month. And that may mean that some months you're going to do preventative maintenance instead of predictive. And you also set it off on a different cycle, so in the future it will be more smooth. Okay? As far as maintenance capabilities versus maintenance demand goes. And so that's a very important concept. The program is capable of creating a digital twin so the client can change parameters such as adding redundant systems. Okay? So now you create a digital twin, and now instead of the sensors feeding in data, we're going to have artificial intelligence sending in data. And one thing we can do is just change time fairly quickly. And we'll change time, but we'll also have all the planned maintenance activities in there. So if you turn this on in time and move it out one month after another, and everything remains the right color, nothing changed to that brown color or red color, it means your maintenance activities has everything under control. And it'll also show maintenance demand, and you can see if that varies much. And if it doesn't, then you say, hey, our maintenance plan is dead on. But if you go along and you see, bang, something starts turning brown and red, that signals saying your maintenance plan is not effective. And you need to go back and figure out what you need to do. Well, let's put a redundant system in here and see what it does now. Okay, that looks much better. Let's do preventative maintenance on this instead of predictive, and change your plan a little bit. Then you'll see it never changes colors. Your actual reliability is always above or equal to the reliability standard. So you can test all of that out. And it'll test it at different temperature ranges, different pressures on the system, etc. You can test all kinds of things. So that's pretty powerful there. The digital twin can also test on best case, expected, and worst case scenarios because it has a tolerance interval, and it'll test at the low, the expected, and the high if you want it to. Very, very powerful. The program can identify when an asset needs planned maintenance activity and schedule the work accordingly. The program can also create and send a PO to the supplier for required assets. It'll check inventory. If there's not enough in inventory, let's get that ordered. The program can also perform risk-based inventory levels for critical assets. And this is pretty awesome. I'm not going to take the time to explain this because it'd be a lecture in and of itself. But we go completely off risk and variability in the supply chain to determine your needs. It's very, very powerful and can save you a lot of money while maintaining your acceptable risk. The program can also create demand forecasts for critical assets should you desire to do that. And we do that a little differently also. We can go out there, AI can go out there and find a curve that matches your demand, only it's maybe 2 or 3 months ahead. So, it will forecast before it actually happens and gives you time to prepare for it. But we don't just create one curve. We'll create one curve, compare the error of that, go out there, the AI will go out there, find a curve that represents that, and keep adding them. What it does is the more curves you add to that to create your demand curve, the lower the standard error is per the central limit theorem if you're into that stuff. But it creates for a much better forecasting tool. And anyway, I could talk about that for the whole time. I'm not going to, though. The program can add baseline sensors to reduce data noise as applicable. Okay? Sometimes in the summer it's higher, so bearing temperatures may show it's higher because it's summertime. Well, we'll create baseline. We'll put a sensor out there to see what the temperature is on the shop floor, and we'll add or subtract that to give you, to send a signal saying, hey, the bearing temperature really is going up. It's higher above ambient temperature. And that can help in many instances. It gets rid of noise in the data. AI leverages sensor data, machine learning, and historical trends to predict equipment failures before they occur, predictive maintenance. Benefits: reduced unplanned downtime, cost savings on repair, enhanced equipment lifespan. Data analysis on predictive maintenance. One thing you'll find with using AI is you're going to have a lot more predictive maintenance compared to preventive, because you have so many sensors that you didn't have before. And so it's going to help you a lot. Now again, we still suggest predictive maintenance, but if you see all these tolerance intervals overlapping on 1 month and say we're in trouble, let's go ahead and change some of those out so you have a little less overlap and help manage your demand for maintenance activities by doing that. The objective of data analysis is to determine if the distribution averages change. What does that mean? It means, did vibration change from this time period to this time period? Did the temperature on this bearing, due to the bearing wear, has it changed from this time to that time? How's it doing on pipe thickness? How are we doing on that, etc. Anything you have a sensor on, oil analysis, for example, is another one. We always check to see if anything changes. And if it's a normal distribution, we use a t-test. And if it's not normally distributed but still predictable, we use a non-parametric equivalent. Of course, you'd rather use these parametric tests. They're a little more powerful. But the non-parametric equivalent still does a great job. Distribution variance changes, so we check for two things. Did the average of the data change, or did the variation change? Either one of those, it will pick up on it and turn the machine red. So that means you need to click on that asset and see what's changed, and then create maintenance activities accordingly. Of course, AI, after you train it, it will come up with its best thoughts on how you should respond to that as well, because it'll look at the tolerance intervals and it'll give you a pretty good idea. Hey, there's a 5% this will fail if you don't change it until this period of time, and you can put in, well, I want to take this risk, and it'll tell you, okay, you probably have this much time then. Worst case, I'd suggest this. And it will give you all that information. AI really is amazing and what it can do for asset management. Reliability will establish the location on the bathtub curve and analyze accordingly. Determine and publish real-time machine reliability. Determine and publish real-time system reliability. Compare actual system reliability to the reliability standard. Identify constraints. It always looks for the highest risk element. And if there's a lot of overlap on the tolerance intervals for failure, it will take the highest risk one and say, hey, maybe you want to do preventative analysis on this one. And it'll do it in priority order based off the mathematics. Create confidence intervals. I should say probably tolerance intervals. Tolerance intervals are single events. Confidence intervals are on averages. And when you're doing predictions, you usually do tolerance analysis. Create confidence intervals for use in the what-if analysis. What is a what-if analysis? Well, what if we change time and this machine has 100 hours on it instead of 50? I want to move everything on the time scale. And when you change that time, there's a little slider scale. You can change time. And what you're looking for is, like I said before, did anything turn red? Did anything turn brown, blinking brown? And if it does, you stop and say, hey, our planned maintenance activities are not working as well. And it'll also tell you demand for maintenance activities versus how much you have available. And if you exceed that, it'll come up in red. And so you're just basically moving the scale on time forward and seeing if your maintenance activities take care of everything according to your risk appetite. And so it's pretty awesome. This what-if analysis is just totally amazing. It'll blow your mind. So it'll show over time to visualize how reliability impacted by redundant systems or more. So maybe you come up with a brown flashing light there, and you're having problems with maintenance demand. So you create some redundant systems on the very critical ones, the ones that changed blinking brown, for example. Let's add a redundant system to that. You can just click on it and say what kind of redundant system you want. Then test it again. Oh, now nothing changes now. Okay, that's much better. That's much better. And etc. So you can test all those things. It's really absolutely amazing what we can do with AI and the data we get. All right, help determine, validate preventative maintenance schedules. And so you may say, hey, that did fail. Let's do the preventative maintenance a little earlier and check it then. So anyway, it's a what-if analysis. All this is what-if analysis. Determine if preventative maintenance should take place before predictive failure based on maintenance capabilities and probabilities. Visualize best, average, and low performance analysis based off of tolerance intervals. Okay. Remember, we have these tolerance intervals. Say 95% of the time it will fail between here and there. Well, let's say it will fail worst case, it fails early, or the expected value, or best case. It can test all of those. And if you want the worst case and prevent for that, then it will allow you to do that. Of course, it's going to cost you more money, right? Because you're going to have to do more redundant systems, more preventive maintenance, earlier, etc. But you can make those decisions based off analysis. All right, failure mode effects analysis. AI helps identify potential failure modes through data patterns and anomaly detection. So, techniques, machine learning classification models, pattern recognition, historical data mining is how it does it. But it can take a given machine and it can give you an exploded view of that machine. And then it can do a failure mode. It can do failure mode, but it can also do the full failure mode effects analysis. And it'll take everything, and you can say, how can this still fail? Give me all the possibilities. Okay, that's the failure mode. That lists every failure mode for every piece of this thing. Okay, how will it affect? If this failure mode is realized, how will it affect it? It'll give you all that. What would cause this to take place? It'll give you all that. In other words, it does the whole FMEA thing automatically. Now, in this system, if the maintenance does experience an unexpected failure, one that they weren't ready for, or any failure for that matter, they'll type it into the system. And that's why it takes some maintenance training so they understand how important this is. And every time a machine goes down or they replace something, they're expected to put in some information concerning that. Because there may be a failure mode that it didn't predict. So now it gives it new data and it will update the FMEA, failure mode effects analysis, accordingly. So it's live updating all of this. And you may say, well, one of the advantages of FMEA is when we do it, it educates us. You're right. So when you have a FMEA and you get a high RPN number, a high-risk element, one of the higher-risk elements on this, it puts it in the control plan. Anything on the control plan means high probability of failure or high severity. And that will be transferred over to the training department, where it can be added to future training. Because if you have something on the control plan, the high-risk elements of a given asset, and you're not training on them, then something's wrong with the whole system. So this is communicating with the training program. But it does the FMEA. You can also go in there and you can look at it after it's finished and just review it and say, hey, you forgot this. And it will learn from that and do better in the future. So it will ask 3 questions for every part on an assembly. What could possibly go wrong? If it does go wrong, how would it impact the process or the customer? What would cause this to happen? Etc. And it will rate every failure mode 1 to 10 on severity, occurrence, and detection. It will multiply them all together to get the risk priority number, and the higher risk priority numbers will go into a control plan, which AI will recommend. The reliability engineer will go through, make sure that makes sense, and add anything. When you add something, it goes back and AI now has it for future analysis. A failure mode database will be set up where maintenance staff will record failures as they take place. As time passes and new failure modes are discovered in the real world, the FMEA will be updated by AI accordingly, just like I just mentioned. As changes are made to the process, AI will update the FMEA data accordingly. AI will recommend various elements of the control plan, high RPNs. It will also give the actions, recommended actions, monitoring, etc. Now, especially at the beginning, you need to look at this and make sure it makes sense and give your input. What are you doing? You're training AI to be better. And it's also looking at your inputs. It's also looking at maintenance inputs on what failure modes were in reality. And it's over time, it's becoming more accurate with its severity, occurrence, and detection numbers, becoming more and more objective over time. In the meantime, it's feeding all that critical information into the training program. Reliability and modeling and simulation. We've talked about a lot of this, but not all of it. AI-driven simulations can model equipment reliability under different operating conditions. We mentioned digital twins, stress testing scenarios, probability risk assessment, etc. And you can have reliability over time. And this may be, for example, vibration over time, or oil analysis over time, or pipe thickness over time, temperature over time, and on the bearing housing. We'll have an equation. It'll say, hey, if you have a higher temperature, then this is going to happen quicker, and etc., etc. You'll be able to understand all these things, and once you have this equation, you can do all kinds of fascinating things with it that's going to save your organization a lot of money. And notice it'll also look for interaction between variables also. That's why you have x1, x2. It's a two-way interaction. And it'll take that into account, and it'll publish an R-squared value. R-squared is how much of this phenomena, vibration, for example, is explained by these variables. Well, maybe temperature has vibration going up quicker. So maybe it'll make sense financially to reduce that temperature for that particular piece of machinery. And it will tell you financially, is it worthwhile, etc., etc. It'll give you all this information. Now, it takes time to create this equation. This equation takes a lot of data. So it's not going to do it on day one when you start it. But as we collect data, it will do this correlation analysis, come up with the equation for vibration, for bearing temperature, for oil analysis, etc., and see how. And if it's statistically insignificant, temperature is, it won't put temperature in there. And it's always trying to increase the R squared value, R squared meaning what proportion of the phenomenon is explained by this equation. And as maintenance puts data into the system, it's always using that data, trying to increase R squared on this equation so you can understand better the nature of your equipment. This is very, very powerful. AI accelerates root cause analysis by automatically correlating failure data, identifying hidden factors contributing failures, enhancing troubleshooting accuracy. And you'll say this happened, and you won't say it. It'll actually go through its own system and find this happened, and it will give you a root cause analysis of all the things that may be cause for this to failure, and it will look in these equations as one place it looks to come up with that. So it's very, very powerful. The root cause of AI is going to be much more objective than what you're currently doing. AI optimizes spare parts inventory by predicting part demand based on usage patterns, minimize stockouts and overstock, reducing inventory costs. This is where we talked about risk-based inventory. And I could spend a lot of time just talking about that, but it's very, very powerful, and it will give you the risk you want with lower inventory levels if you do it correctly. It's all about variation in time in the supply chain. And AI takes all that into account. Human reliability. AI enhances human reliability by monitoring operator behavior and fatigue, providing real-time decision support, training simulations, and augmented reality aids, etc. AI evaluates warranty claims and field performance by analyzing failure data trends, identifying systematic issues, improving future product designs. Again, it's going to always try to drive that equation of warranty claims equals beta, and all this with an R squared value. Very powerful. Conclusion: AI is revolutionizing performance management in heavy industry by enabling smarter, data-driven decisions and enhance reliability, reduce costs, and extend equipment lifespan. It truly is a revolution going on here. The way you're doing business today is not going to be how it's done tomorrow. And if you keep doing it as you're doing it today, you won't be competitive enough to survive in the marketplace. It is amazing. And to me, it makes your work life better because you're going to spend more time on more important things than you've ever done in the past. Key benefits summary: reduced unplanned downtime through predictive insights, lower maintenance costs with optimal timing and planning, increased equipment and life and system reliability, smarter spare parts inventory and procurement decision, enhanced safety and human reliability awareness, faster and more accurate root cause identification, digital twin simulations for proactive decision making. Implementation roadmap. On this program, we don't just sell you software. We come in as a team and help you set it up. Because if we don't, your probability of failing is much greater. But here's the part of the implementation roadmap. Assess current equipment and sensor readiness. Do you have all the sensors you should? There's a lot of sensors out there that can really help. Without the sensors, this isn't going to work, because that's where we get all the data. Implement data collection and integration infrastructure. Train AI models on historic and live data. Validate reliability models and simultaneous simulation outputs. Roll out predictive maintenance and alert systems. Incorporate digital twins for ongoing decision support. Continuously improve models with new data and feedback. And that's a big one. It's constantly improving, constantly becoming smarter. Well, congratulations, you made it through that. Hopefully you learned something new. If you have any questions, you can most certainly look at my website, www.alphaqc for qualityconsulting.com. And there's a page on there called Reliability Training. And You can learn more about that this is the direct link, or you can just go to alphaqc.com, select the Reliability Training tab. If you have any questions, please contact me. There's my email address and there's my phone number. Thank you very much for joining me. I hope you learned something that will enhance your career. Thank you, and have a great day. Goodbye.